starting the runs. Hello everyone, welcome to this seminar on computer architecture lecture. Today I'm going to talk about one topic that is quite related to my PhD dissertation. So I'm a PhD student in the Safari Research Group in my last year. And today I'm going to talk about memory-centric architectures, which is a topic that I've been conducting research since I started in 2018 over here in the Safari Research Group. So this is quite a long presentation. So I'm going to cover a lot of works, but don't feel overwhelmed about them. I don't expect anyone to get the details of the mechanisms. It's more for you to have an idea of different type of memory-centric architectures. Of course, my point does not work anymore. Okay, so the main problem that we're trying to solve with memory-centric architecture is that today computation is mostly bottlenecked by data. And data is quite important for many different applications from varying domains. So, for example, we have various applications like machine learning workloads, genomic workloads, or databases that the amount of volume of data that they produce and consume is increasing and increasing over time. So, for example, this is an example of the memory requirements that we have for neural networks over the time. So you can see the x-axis here, the memory requirements in gigabytes, and the total training that is used for different transformers, neural networks over here. And then you can see that there was a huge jump from BERT, for example, to GP3 of almost 3 orders of magnitude more memory requirements over the time in the last 2 years. So this is also true for other application domains like database, graph processing, data analytics, and data center. And what we are seeing today is that because of this data movement bottleneck, or this requirement of large amounts of data for application to consume, we are seeing performance and energy overheads created by moving the data across the system that those applications run. So we did some study in several workloads, for example, in mobile devices. Here we have Chrome, TensorFlow, YouTube video playback and video capturing. And then again, over there, even though all of those applications were running on edge devices, for example, on your phone, not in data centers, still the data was key limiting for performance and energy efficiency for those mobile applications. Again, this is true for other domains as well. So in the bioinformatics domain, for you to sequence new virus or new portions of the human genome, we require more and more data over the time. And this is particularly important for this genomic analysis application domain, which is key to understand new disease and create new drugs to solve those diseases quickly, as we saw, for example, during the COVID pandemic. And again, data movement is a key limiting factor as well for genomic analysis. So why data overwhelm other systems, or where? So there are many reasons. So it can be because of the size of the data that you want to store, the data. So you have terabytes or petabytes of data that you need to store if many SSDs stored in DRAM, or because the communication capabilities across those different memory devices inside the memory hierarchy itself, or because of the limited computing capability that you actually need to execute on top of that large amount of data that you are consuming. So all of this greatly impacts the robustness, energy, and performance and efficiency of current systems. So all of this is tries from the fact of how we are designing computers. So we design computer systems today following what's called von Neumann architecture. So in a von Neumann architecture, we have three main components. We have computation, communication, storage, and memory. And even though this model has been proposed in the forest, we are still doing computation or still designing systems mostly in the same way. So we have your computation unit composed of CPUs, GPUs, accelerators. And over the time, when you look, for example, of a CPU, you have this type of view over here, where large portions of the system itself, so the green boxes here, are dedicated to either for the storage or memory of the system, or to move data across the system, while the red parts here, so a small percentage of your system is composed of actually computing cores. And so if you look at even further more and more modern computer systems, so for example, if you have, this is a AMD Razer processor with a lot of cores. If you look at this green area here, or which is, I don't know, roughly 80% of the chip, you're going to see that you have most of the die dedicated to storing data, so for the L3 caches. This is a trend. We are seeing more deeper and deeper caches on your system. So this is another example for this AMD processor that has 64 megabytes L3 cache using 3D step integration. And this is another example for another architecture from IBM, again, where the majority of the die itself is dedicated to the caches and to moving data around the architecture. And this is yet another example for Apple. It's quite old at this point, is the M1 processor. So what we have over there basically is a lot of SRAM dedicated for caches, a lot of DRAM dedicated to store data, and more storage dedicated to store temporal data. So we conducted a study, and then we saw that by designing systems using this von Neumann architecture, we spend a lot of the total system energy moving data around those caches and storage and memory devices. So this study, we saw that for these mobile systems, 62% of the total energy was spent actually in data movement. And this is not only true for your phone or for your computer. So if right now ML is machine learning is quite an important application, and over there we conduct a study on tensor cores for accelerating neural network inference, and we saw that more than 90% of the total energy for some of those for some particular ML models were spent only moving data across the system. So what is the problem that you have is that the data is the main bottleneck in terms of performance and energy in today's systems. And this is caused by the way that we are designing the systems. So we are following this von Neumann architecture, which by separating the system into compute, storage, and communication, we are having balance in the system, leading to energy and performance loss. So just to summarize, the main, if you look deeper of all of these problems, is that processing of the data is usually performed really far away from the data itself. So the processor is the center of the communication in the entire system, and then we have many levels in a deep cache, in a deep memory hierarchy where we need to move data back and forth all the time. And this basically causes a huge cost for the system. So this is not a new observation. This is not a new problem. There is this seminar paper written by Richard Sykes in 1996 that has this really nice title, is The Memory Stupid, that over there, already in this 96, the 90s, he already said that he expects that in the coming decades, the memory subsystem will be the only important design issue for microprocessor, because exactly of this imbalance that we saw over the years on terms of the amount of resources that is dedicated to computing versus the amount of resources dedicated for storage. So this is just a study over here that Professor Mutlu did when he was doing his PhD. And basically he was at Intel, and then he took several applications that were of interest of Intel. He profiled these applications, and then we saw that he had this most of the execution time spent for those applications is dedicated on memory access. And there are solutions to solve this problem. But coming back to the problem itself, so that study that he did was 2003, and then looking back into looking in the future in 2015, so many years after that, Google conducted this study providing a warehouse scale computing, where they look at their data center applications, and then they saw that the majority of the time for several of those data center applications were again being spent on moving data around the system. This is just another view of the same data. So, so what is the main problem that we are seeing here? Again, is that this imbalance that we have in the system on this volume architecture is causing problems in terms of energy efficiency, performance, and complexity in order to design efficient systems today. And then to tolerate this inefficiency, you are actually designing even more hardware on top of what the already existing hardware that is just there to try to mitigate this data movement issue, or moving the data across the different elements of the hierarchy more efficiently. For example, with aggressive hardware prefetchers, or deeper and deeper cache hierarchies, which again just create more complexity and more imbalance to current processor designs, and it becomes a vicious cycle basically. So in terms of energy, if you look at the total energy that it takes to do computation compared to the energy that it takes for a memory request, you are going to see that a memory request takes $2 to $3 of magnitude more energy to compute a complex addition operation. So this is another view of the same data. So here in the x-axis you have the energy normalized to the rectifier axis to perform different type of operations. So we have multiplication with using integers, or multiplication using float points, as a cache access and a DRAM access. And you can see here that this data is from another type of processor, but again we see that we have a threefold order of magnitude more energy being spent on data movement compared to the integer computation itself. So data, so this just wants to make us to conclude that in order to minimize energy consumption in current systems, we need to minimize data movement, or we need to avoid moving data outside or even inside the architecture itself. So to accomplish that, we actually need a paradigm shift. So we need to think differently from the traditional von Neumann architecture. And we need to design systems that can mitigate the amount of data that you are moving to perform a particular algorithm or a particular test. And the main idea overall is to compute where the data resides. So if the data is already in our DRAM, ideally, we will never move the data out of the DRAM chip. We are going to, because as I showed earlier, computation is much cheaper in terms of energy than moving the data out of the DRAM chip itself. And if you design systems following that philosophy, we are going to have what's called those data-centric architectures. So a data-centric architecture is an architecture that handles data well doing a particular computation. So how to do that? How to handle data well? So the first thing that we need to do is that we need to ensure that data does not overwhelm the other components of the system. And we can do that by different approaches. So we can have better algorithms, we can have better architectures, and we can co-design the algorithms together with the architectures to enable a more efficient system. We also can take advantage of the data itself to allow the system to be more aware of the properties of that data and how the data should be treated using either metadata or of better learning or better heuristics that use the characteristics of the data for computation. And also we can understand and exploit the properties of the data to improve algorithms and architectures today. So, as a summary, we have basically in computer systems today this processor-centric view, where we are going to move the data near to the computation, versus this data-centric view, where we are going to do the computation nearby where the data is. And this, by designing these different systems in these different with different approaches, this is going to dictate what type of design we are having. If you are having a designer dictated decisions, or if you have a more data-driven decision. And also you can look at the data itself and have a more data-aware decision. So look at the properties of the data versus following heuristics that are oblivious to the characteristics of the data itself. So overall, what we want to design better systems, we want a more data-centric architecture, architecture that is data-driven and is aware of the data that's been computed. And there is this talk that is called Intelligent Architectures for Intelligent Computing Systems, where those components are elaborated. So basically, if you want to design these more balanced systems, we need to revisit how you are designing systems today. And to do this, this revisiting to implement such more efficient and intelligent systems, we need to have a holistic view and look from both how you are designing algorithms to how you are designing the interface between these algorithms and the hardware, and how you are designing the hardware itself. And this leads me to talk about the implementation of data-centric or memory-centric architectures. So what are the main properties of those data-centric architectures? So the first one, as I mentioned several times, that we are going to process data where the data resides. So we are going to avoid moving data as much as possible, so we can have the second property, which is low latency and low energy access, low energy spent on data movement itself. We also want to have a low cost for data storage and processing. So we're going to look at ways of improving the capacity of a memory system, so that we can feed more data and eventually enable more computation over the data. And also you need to have more intelligent data management systems to control and to coordinate properly how the data is being processed and moved across the system. So let's look at the first component, processing data where it makes sense. So this is again the same view of the M1 chip over here from Apple, and again we have a bunch of components being dedicated to storage, or to memory itself. So where does it make sense to compute? It doesn't make sense to move a portion of data from the storage side down to the CPU, or to just offload the computation to the storage itself, and possibly avoiding data movement costs. So to do that, basically we need to think differently from the past approaches. So what we're going to have for these memory-centric architectures, or the designing mindset that you're going to use for these memory-centric architectures, is this idea of thinking about memory not only as memory or not only as storage, but also as accelerator, where we can offload computation to this accelerator itself. So this is quite similar to a conventional accelerator. So let's say that you want to have a query in your database that you want to figure out some properties, and then instead of moving the data out of the database storing memory to the processor to compute that query, I'm just going to tell my memory itself please return from this database all of the students that live or are from Switzerland. And then I can do the computation and the query inside the memory itself, and then the data was only going to return the output. So there is no intermediate data being moved from the memory to the accelerator itself. So this is ideally what we want. We want to tell the memory what we want. I want to query the memory with some information, and then we want to retrieve that information without having to move the data outside the memory itself. So this is, we don't know, we are in 2024, it's quite an old idea. So this concept of memory-centric architectures, or another way of calling this processing in-memory architectures, have been proposed initially in the 70s. So those are some seminal works that talk about this idea of memory as accelerator device itself. And over the years, we have seen many attempts to implement such architectures or make them commercially available. So this is a paper from the 1997, which is try to create this architecture called IRAM, which is exactly what I just mentioned, was a accelerator type of memory. So why should we look for memory-centric architectures today? Basically, we have three main pushes. So the first one is that we have this push from the application domain, of the memory technology domain itself. So memory is scaling memory becomes more and more complicated. So when you have your memory chip, for example, your DRAM chip, and you start reducing the size of the transistors, we see some problems related to reliability and security and the efficiency of that memory device itself. So scaling in terms of technology manufacturing has become a much more challenging factor. So we also have this demand from applications and systems. So this is what I've been trying to motivate so far. So we have this data movement bottlenecks caused by this large amount of volume that current applications are processing and generating. And at the same time, we have a push from the need to have being more performant or being more energy efficient and sustainable when doing computation. So at the same time, we have and when you put it together as a designer, we are squeezing the middle. So we have, from the technology point of view, we have worsened technologies in terms of scaling, and from the application point of view, we have more and more demand from that application requiring better technologies. So there is a push, or there was a push, there is still a push actually, from the industry itself to try to figure out at least the memory scaling problem. So this came around 2012, 2015. Micron and other companies create this Hybrid Memory Cube consortium where they start developing what's called 3D stack memories, where you stack together different dies of memory and then you connect them via what's called 3 silicon vias. And it was later on followed by other technology, like if you look at, for example, NVIDIA GPUs, you're quite familiar with this high bandwidth memory type of architectures, HBM, which are quite popular for machine learning. Micron also released this automata processing prototype over the time. Other startups are also looking into this landscape, this possibility of memory-centric architecture. So we have this French company called UpMem that they create these DRAM teams that are composed of both memory and some other cores in the same package, and they can do computation here in the memory itself. Samsung has announced it in 2021 following this 3D stack organization. Some processing memory accelerators for neural network inference, particularly transformers. And recently, last year, they announced three or four more prototypes for the same system. So the interest is increasing, and Samsung is not the only memory manufacturer looking to this. For example, other memory manufacturer called SK Hynix that is also designing accelerators using memory devices targeting machine learning in fields. So there are many more. There are more prototypes from Samsung and for data center systems like or companies like Alibaba. So even though I'm going to do a quick detour to talk about these memory scaling problems that I briefly mentioned. Again, the problem that we have here is that we are packing more and more transistors inside a memory package or a memory chip itself, and this is creating some reliability problems. So there is this curious phenomenon that current DRAMs or current memory systems face, that one can predict or induce errors or bit flips in memory chips itself by doing what is called a RowHammer attack. So the way that this is done, so in the memory chip, we have several DRAM rows inside the DRAM array itself. So one of the rows it stores your data, and the operation that you do to read the data from the DRAM chip is called activation or the opening of that row. So these prior works have shown that if you continuously open and close the same row several times, you can generate bit flips. You can in the nearby DRAM rows, and this is called this RowHammer attack. So basically, the main issue behind, or the main thing that is actually enabling such bit flips to happen, or this is the effect that's called read disturbance to happen in current DRAM chips, is because of the fact that we are packing the cells for those different DRAM rows super close to each other inside the DRAM array itself. And many security papers have used or exploit this phenomena to, for example, take over a computer or to reveal secret information from user space or for user data. So we did this study back in 2014, and then we saw that for three major memory manufacturers that share the majority of the market, we can induce these bit flips by following this RowHammer attack quite successfully with quite a high success rate. And this attack, this type of exploitation, gain a lot of traction after that. Those initial works have been done. So Google also tried to study this RowHammer effect, and they also released like a paper after or around the same time that the other paper was released. And the question is, so all of these works were done in 2014. And so I'm looking for these other slides, which is not here. So all of these attacks were done in 2014 for mostly DDR3 chips, and then later on we revisit more modern DRAM chips themselves to see if this RowHammer problem was solved after the initial publishing of that paper in 2014, and we saw that the problem, even in modern DRAM chips, was still not solved. Actually, it's becoming worse and worse as we scale the size of the transistors to a smaller technology node size. So if you are interested on this type of security aspect of memory systems, I invite you to check this paper, Fundamentally Understanding and Solving RowHammer, and there are also some lectures online talking about the security aspects of the DRAM itself. So I don't know if there is any question at any point on YouTube or here, so feel free to stop me if there is any. So yeah, so there we have many lectures and classes related to the security issue. So going back from the memory-centric architectures itself, so there is this push from the technology aspect, where the memory subsystems are becoming more error prone, and to mitigate that, we basically need to either design better memories, or we can mitigate those problems by designing more intelligent intelligent controllers for those memories themselves. So this is one example of a mechanism or intelligent controller which can prevent those RowHammer attacks by throttling access to those to DRAM rows. And there is only not there is also examples from other groups that are looking into this how to design these intelligent controllers to mitigate these errors caused by RowHammer. So this, for example, one proposal for this other memory manufacturer that was presented in 2023. And this is just an excerpt of them and the view of what basically they are doing by using some tracking counters to figure out which rows they should avoid access. So yeah, there are more other examples of intelligent memory controllers, and after we did that initial RowHammer study, later on last year, actually, we figured out that it's not only by accessing DRAM rows simultaneously that we can induce bit flip. If you, for example, just keep a DRAM row open for enough time, we can also experience bit flips on nearby rows in this phenomenon that we are calling row press. So basically, this is just to say that this reliability issue of DRAM is not only not improving, but also getting worse and not worse only because of RowHammer. There are other phenomena or other rich stubborn phenomena which now we can produce again because of this scaling problem. So this is the row press architecture. Industry is also looking quite deep on this scaling problem of memory devices. So Intel and Samsung wrote this paper together, talking about the challenge of scaling DRAM to smaller technology nodes and what can generate it. And there is also this other paper talking about how to architect better controllers to mitigate these DRAM scaling problems. So the main takeaway here is that we need to implement more intelligent memory controllers if you're not going to fix the scaling problem, at least to mitigate such scaling problems. So going back to the memory-centric architectures, again, what we want is a system that is high performance, energy efficient, and sustainable all at the same time. And to do that, we are going to design systems where computation is done where the data resides. So again, our goal here is to query my memory device. We call that we are treating the memory as accelerator, and independent of the application that we have, we want the processor to just query the data with some information, and then the memory returning that output data or the results to the processor without involving moving the input data down to the processor for the computation or intermediate data as well from the memory to the processor for computation. Okay, this is it seems quite nice and it seems quite powerful setup, but there are many design challenges that we need to figure out in order to design this type of architecture. So, for example, what type of computation capability we give to the memory device, because we don't want the memory to be as powerful for computing as the processor, because that would be quite challenging to manufacture because of thermal limitations and costs related to manufacturing. So how you communicate across those units, what is the hardware and software interface that we need to allow the processor to communicate with the memory, what are the type of compilers and programming language that we need to use for this type of systems, and what are the changes in the algorithm that we need to do to enable this type of computation. And again, all of this requires a holistic view of the computer architecture stack. The next part of this in this lecture, I'm going to talk about different implementations of these memory-centric architectures for varying applications or application domains. And all of this is based on this book chapter that is called A Modern Primer of Processing Memory. It is available in your webpage. So if you are interested on reading more or more details on the architecture that I'm going to talk next, please check it out. So before I start talking about the architectures themselves, I'm going to give some taxonomy of the different architectures, or how you classify those architectures. And again, we are calling these memory-centric architectures processing in-memory architectures, and we are going to see two different ways of implementing processing memory architectures. The first one is what we call processing near memory, and the second one is what we call processing in-memory. So we have these two approaches of processing in memory, this processing using memory and processing near memory. We are going to start with the near one. So in the process near memory approach, we are going to add logic nearby the memory cells themselves. So think that you have a memory array and you have a processor. We are going to take a simple version of that processor or a simple version of accelerator, and we're going to embed the memory chip itself, a memory DIMM, or a 3D stack memory with that accelerator. So you're giving some logic or computing power to the memory device. Then one of type of applications that benefit from this type of design is graph processing. So graphs are everywhere, and from Wikipedia to social media. And usually the type of computation that we do for when you are traversing to graphs is quite small. So you do very little amount of computation, and you incur a lot of random memory access when you are traversing large graphs. So we have this opportunity of leveraging these new 3D stack architectures, where again have several layers of memory connected together with a layer of logic. And since these memory and logic layers are manufactured in different processes, and later on they are connected together, basically we can design some computing logic inside this logic base here to accelerate given application. In this paper that we presented in 2015 called Tesseract, we look at the opportunities that these 3D stack memory architectures provide, and we to accelerate graph processing applications themselves. To do that, we designed this network of these 3D stack memory architectures. And inside each node of this network, we have your regular DRAM controller, and we embedded some simple encoder cores nearby in this the DRAM controller itself, in this logic die over here of the 3D stack memory itself. We also have some auxiliary hardware to compute in a distributed way across this network of memory devices here. And we also have some prefetching to exploit or to improve the memory level parallelism that you have for the systems. So we evaluate this architecture using traditional systems, and also two other implementations of a system using these 3D stack architectures in a compute-centric way. And then we see that compared to all of those systems, we can have way more bandwidth for this graph processing application, which actually translates to performance. So overall, by doing this, by having simple encoder cores near the memory device itself, we can accelerate graph processing by around 13 times. And so this is also another view of the result. So this is the energy result, and we see that by moving the data nearby this logic layer inside the 3D stack memory itself, we can reduce energy consumption by 8 times for graph processing. So again, if you are interested on this paper, I invite you to check the Tesseract paper. And there are other examples of similar systems for other applications. So the Tesseract is using DRAM and this 3D stack memory device to do computation. But we can also think of the same architecture, the same type of design, using other memory technologies, as for example, flash devices like which are non-volatile memory devices. So we look at the problem here of genome. You have a question?
Yeah, sorry. Sure. So the Tesseract system is only for graph processing.
Graph processing, yes.
So you can't execute like other.
In theory, you can, because since the cores that we are using here are simple in all the cores, and those cores are general purpose. So in theory, you can accelerate other things, but it was designed initially having graph processing algorithms in mind. Okay. So this other one here is a bit more restricted because it's targeting genome sequencing analysis. So when you're doing genome sequence analysis, so your initial reference genome is stored in these flash devices, and before doing anything, you need to move this genome data to your compute units, and the genome data is some gigabytes or terabytes worth of data. And this creates some computation overheads and data movement overheads. So there are some accelerators or based on some heuristics or some hard designs or some filters that is trying to move the amount of computation overhead that we have when you're doing this genome computation. But still, regardless, you need to move the data out of the storage to the computing units before doing anything. So the key idea that we had for this work, to accelerate this genome sequence alignment, is to use the storage as a filtering engine. So you're going to perform some filtering algorithm to the genome data inside the storage device itself. This is going to basically prune the amount of useful portions of the genome reference genome that you're going to use before computation to only some small segments of that data, and then we can only move that small segment of data to the computing unit or to the accelerator, which basically reduces the computation complexity when you're doing this genome analysis before the computation. And this, with all of this, we can maintain the fact that we can accelerate the computing or reduce the computing overheads of the genome sequence analysis, and together we can reduce this data movement traffic that is required for this sequence alignment step. And we evaluate the system, and you see that by doing so, we can significantly improve performance while reducing energy at quite a low cost. And this is this paper called Genome. So yet another realization of these memory-centric architectures. Now we are going to look at mobile devices. So in the first one, we were looking at graph processing. The second one was designed for genomics, and now we are going to design a system for consumer devices or mobile workloads. So basically, we saw that first of all, when you have your mobile device, so you have your Apple Watch, or you have iPhone or Samsung phone or your tablet, battery or the battery life or energy that's spent for running something is quite important, right? So you don't want to constantly have to charge your device. So we look at these 4 popular workloads that you run in your iPhone, your phone, for example, and then we did some analysis of them, and then we saw that for several of those applications, 62% of the total energy in the system is spent just moving data across the memory hierarchy itself. The second observation is that this data movement or this energy spent on data movement comes from executing really simple functions or really simple computation. So we don't need powerful processors to accelerate those functions. So similar to the Tesseract system, we can embed the memory device with simple processors or lightweight processors or lightweight accelerators to accelerate the execution of those functions, those data intensive functions inside the memory device itself. So looking at the workload analysis, so this is the TensorFlow mobile workload, and we did some analysis, and we saw that the inference energy is heavily bottlenecked by data movement, and this data movement comes from this packing, unpacking, and quantization function that these TensorFlow models were generated. So by accelerating these simple function units, by accelerating those simple kernels. So for example, here the packing and unpacking that I just mentioned here, with the spin cores or the spin accelerators engines inside the memory device itself, we can reduce energy consumption by around 50%, while improve execution time by around the same margin compared to the your regular CPU implementation. So this is this Google workload for consumer devices paper. We can do the same, for example, for GPUs, or so those three, or for other pointer chasing heavy workloads. We can or for to accelerate dependent cache misses, or some perfection techniques. And so those are just examples of those processes in your memory architecture. So also for weather prediction, so for some similar problem, approximate street matching for sequence alignment, genomic sequence to graph or sequence to sequence mapping, base calling and read mapping, time series analysis, graph processing, some database operations, and for neural network models running in edge device. And for those, I'm going to again briefly talk on those in more details. So basically what we did in this project, we analyzed 24 different models from Google neural network edge models. And then we saw that they suffer from three main challenges. The first one, they operate those models when running on the Google accelerators. They operate below its peak throughput, also below its theoretical energy efficiency, and also they handle memory access quite inefficiently. So the key insights that we had when looking at the design of the Google accelerator is that those issues come from the fact that the accelerator is a monolithic design. So there is one accelerator that is designed with a fixed size, and this accelerator is trying to fit different type of models which have different properties. To solve this issue, we proposed this mechanism called ENSA, which is a heterogeneous set of accelerators specialized for the different characteristics of the layers inside those neural network models. And by implementing these accelerators using this near data processing or processing near memory type of architectures, we can improve energy and performance compared to the baseline HTPU accelerator. So this is just a representation of what we did. So Google has this accelerator is an edge accelerator for neural networks called the Google Edge GPU. And basically, the accelerator is designed to run different type of neural network models. For example, recurrent neural networks, or LSTMs, or CNNs, or CNNs, and all those models, of course, are used for different tests. And when we analyze those models, we saw they have significant variation in terms of property, for example, in terms of their memory footprint, or in terms of their computing, the arithmetic computing that they need to achieve to do the computation. And they also have significant variation inside a single model in terms, for example, of the number of multiply and accumulate operations that they do depending on different layers of those models. So basically, there are variation for those models, either across models and variation for those models inside a single model itself. The solution that is out there right now is to take all of those models, dependent of their size or characteristics, and map them to a single monolithic accelerator. But we see that if you design smaller accelerators that are targeting different types of properties for those models, and efficiently map the different layers with those different characteristics down to the appropriate accelerators, we can have a system that is more energy efficient, performance efficient, and area efficient compared to the monolithic accelerator. The key observation that we do is that basically we don't want to design as many accelerators as we have layers in the neural network models, because that would be quite wasteful. And the first observation that we do is that actually the layers tend to cluster into two main families. So the first families of layers are those compute-centric layers. So those layers does a lot of multiply and accumulate operations and have really high reuse of data, while some other families are more data-centric. So those are memories. Those layers have lower number of multiply and accumulates. They have lower amount of reuse, and they have higher memory footprint compared to this compute centric. So in theory, if you design two accelerators covering those 5 different families of layers, we can have a better and more efficient system. So we do that. We implement actually 3 accelerators, because there is a special case for LSTMs. But basically design accelerators, and then we see we can significantly reduce energy consumption compared to the monolithic HTTP accelerator, and also improve inference throughput compared to the baseline HTTP accelerator. So this is this Google neural network paper. There are again other workloads that you can accelerate using the same approach. So in all of the prior work that I showed before, we are taking entire application and trying to, or entire function, and trying to map it down to a accelerator. But we can also think about just small instructions. So we have atomic operation, like atomic addition, that you want to accelerate or offload to the memory device itself. So it's also possible to change the granularity of computation that you want to offload to the memory, and this leads to different trade-offs in terms of performance, energy, and area cost. So we also did some analysis for FPGA-based near data processing accelerators, and all of those were more academic studies. So we did that using simulation. But as I said, there is a huge push from memory manufacturers themselves to look at these memory-centric architectures. So I'm going to talk briefly about some of those real processing memory architectures that are out there. And I don't know if you can directly go to Digitech and buy one, probably not at this moment, but they are getting traction in the market over the time. So the first one is this system called UpMem, from this I mentioned before, this French startup that was released in 2019. And basically what they do is that they take a memory DIMM. So this is a memory, I think there is a better picture here. Yes. So this is a memory DIMM, and inside this memory DIMM you have several memory chips. And inside these memory chips we have some simple in-order cores that are capable of implementing some general purpose computation. So these UpMem systems, they compose the entire system out of these memory computing capable DRAM DIMMs. So here you have the CPUs, we have your regular DRAM, you have these their memory models capable with these computing units, and basically if you look inside the memory unit itself, there you're going to have your regular, what's called DRAM bank, which is a regular portion of your DRAM to store data. But you also have some simple other processor with some instruction and working memory here that is capable of doing some simple, not necessarily simple, but to do integer computation for different applications. So we did a lot of studies on this PIN architecture, this PIN architecture. We generate benchmark suites for them, which is called the Spring benchmark suite. We also try to port different applications, for example, machine learning training down to these applications using different application optimizations. And this is if you're interested in the talk. And We also look at how we can accelerate sparse matrix vector multiplication on those systems, and also sequence alignment, and also also sequence alignment. I think I'm missing here the other work that we did for programmability of the systems, and also for transcendental functions implemented inside this memory device itself. So basically, the summary here is that, yeah, they have these real process memory architectures out there, these automated systems that can execute general purpose applications, and then we are basically taking different applications for various domains and then mapping down to these systems, and usually we see some performance and energy savings when doing so. So this was from UpMem. So Samsung in 2021 also released its own version of this type of architecture. Samsung initially called it film DRAM, but later on it changed to HBM PIM, and I think it changed it again to Aquabolt later on. So in this UpMem architecture, in this film DRAM architecture, the implementation is a bit different from what I just mentioned from UpMem. So here we are not using DIMM, so we are using 3D stack memories, and we are going to repurpose some of the layers of the 3D stack memory to do computation. So this is the computation that we are going to do. Is a quite simple SIMD engine that is targeted to implement some multiply and accumulate. Multiply accumulate operations targeting to accelerate neural network inference. So they actually implemented this system, and they after the implementation of the system, they keep releasing a follow-up approach of this architecture since 2021. So in 2023, Samsung released other versions of this HBM PIM architecture or film DRAM architecture targeting generative AI or transformers. So the main takeaway that they do is that when you have transformers, we have a memory bound step, which is called generate, and this step is quite bound by general multiply general matrix vector multiplication, which takes around 60 to 80% of the total execution time. So this is a breakdown for a given model, and you can see here that the latency of this generation step taking a lot of execution time for computation. And Samsung proposed, if I'm not mistaken, 2 or 3 solutions for this problem of this GMV operations. So the first one is this AMD M100 GPUs fabricated with HBM systems here. So basically, they take that HBM PIM architecture, and then they use it as memory for these AMD GPUs, and then they offload the computation of the generative step to the HBM systems, and they see significantly improve energy efficiency and performance for some transformer models. So they accelerate GPT by more than 2 times over the baseline. The second solution that they propose is targeting mobile devices. So now they are not going to use these 3D stack memories for computation. They are going to use what is called low power DDR memories. But again, they are basically going to take these low power DDR memories, and they are going to add the same SIMD engine that I mentioned before from multiply and accumulate from the MIM DRAM architecture to the inside this low power DRAM chip architecture. So you can see those units over here, and then again they accelerate GPT-2, and then they see significant performance and energy gains compared to the baseline system. So the third solution is using what is called CXL. So CXL is an interface that allows you to interconnect several memory devices together. It's a consortium from memory and several manufacturers that they came up with this standardized interface. And what this allows you basically is an easy way of scaling up the capacity of your memory system. So So you have basically this memory expander here, which you can just put in your system, and this memory expander has a controller and several memory devices. So Samsung really proposed two versions or two implementations of that HBM architecture following this CXL memory expander. So one is adding pin units in the controller of this memory extender, and the other one is on the memory device itself. And by doing so, they can offer a 4.4 higher energy efficiency and a higher throughput than GPUs. There's another version of a different accelerator, but also from Samsung. This one here is targeting recommendation systems. It's called XDIMM. So you have again a DIMM here, and each chip of these are different memory chips. And inside these memory chips, what we have is basically some really primitive logic to do embedding computation for these recommendation applications. Other memory manufacturers other than Samsung, like SK Hynix, also released recently 2022 their version of process memory system. Is in terms of overall architecture is quite similar to Samsung. We have several DRAM banks connected to some logic. They can do that's starting to do some multiplication and some addition. Again, targeting neural network inference. And this is the other system that was released in the same year by Alibaba, also using some logic for recommendation systems. So here the technology is a bit different. They use what's called hybrid bonding. So they have two dies that are manufactured separately, and then later on they merge those two dies together in a single package, and this allows them to basically do this entire system together. So all of this, I don't know if there's any question for this processing near memory architectures. But if not, before entering into processing using memory, I'm going to take a 10 minutes break, and then we can resume afterwards. Okay, so let's go back to processing memory. So now we are going to talk about processing using memory. So before you're adding computation near the memory to do different operations for graph processes, for neural networks, for bioinformatics. Now we are going to think in a more radical way. So we are going to try to use the memory cells, so the storage used to store data, to do computation. So not only to store data itself. So let's start easy. Let's say that we just want to allow to copy data from one row to another row inside the RAM, or initialize a row with some ones or zeros without having the intervention of the CPU in that operation. So you don't want to have to move the data around. And this, even though this operation seems quite trivial, they are quite used for many type of portions of a system, like forking different threads, checkpoint, page migration, and many more. So how you do that if you want to copy one row to another row in today's system? So you access the first row, and then you move that row piece by piece to the memory, to the processor, and then later on you move the data, the destination data, from piece by piece from the memory to the processor. You do the copy, and then you write back. So this incurs a lot of latency because you are moving segments of that row at a time to this limit size bus over here, and also it reduces the it requires a high bandwidth utilization of the share bus. It creates cache pollution because you are putting data in the cache just to copy one to another, and overall there is this unwanted data movement from one system to the other. So in terms of energy, if you do that operation in today's systems, you are going to take around 1,460 nanoseconds or 2.6 microjoules for copy 4 kilobytes page. So what we want a way of just telling my memory device, copy one row address to a destination row address without moving anything out of this memory device down to the processor. So this allows us to do this data copy with low latency, low bandwidth utilization, no cache pollution, and no unweighted data movement. And compared to that latency that I just mentioned for the traditional way of doing this row copy operations, we can reduce the latency of copy 4 kilobytes of data from 1096 to 90 joules, and the energy for 33.6 to 0.04. But in order to explain how you can do that operation, I need to briefly talk on how DRAM operates, because we are going to use that operation principles to do that data copy operation. So the main thing that you buy when you buy a DRAM DIMM is a DRAM module, and inside the DRAM module you have several DRAM chips, and inside the DRAM chip you have several DRAM banks. So inside the DRAM bank, we have a 2D array of DRAM cells called a DRAM subarray, where horizontal rows are connected to a word line and vertical columns are connected in a bit line. So the bit line shares what is called a sense amplifier, or are connected to a sense amplifier, and a set of sense amplifiers is called a row buffer. A DRAM cell itself stores data using a storage capacitor. And to access this storage capacitor, the DRAM cells use access transistors, which connects the word line to the bit line. So this is just another view of the same system. So you have here the DRAM chip, have some I/O, and then you have the banks. And inside this bank, there is not shown here. We have the subarray, and then inside the subarray, we have the different rows of DRAM cells and the row buffer. So in order to access DRAM, the memory controller issues 3 main operations: the activate, read and write, and pre-charge. So let's see how this works. So doing the activate command, the memory is going to assert the word line connecting the storage capacitor to the bit line. This allows the storage capacitor to lose charge to the bit line, generate some perturbation to the voltage level. The sense amplifier is enabled and sense this perturbation in the bit line voltage level, either to VDD or to ground. And this sensed perturbation is amplified, and the data that is amplified is restored into the DRAM cell itself. So after the data is accessed or activated, the row is activated, the data is latched to the sense amplifier or to the local row buffer, and then the DRAM chip, the memory controller can issue several read and write requests to read portions of this data that is latched in the sense amplifier. So in the end of the operation, to allow for a next DRAM access to the same DRAM array, the memory controller issues a precharge command, which basically lowers the word lines, connecting the word line to the bit line, precharge the bit lines to a reference of voltage level, which is RVD, for a next access, and the sense amplifier is disabled. So again, what we want is to allow the memory to simply copy one row to another without intervention of the processor. And what we are going to do is we're going to follow those activation and precharge command that I just mentioned before to do that operation. So here we have a DRAM subarray with many rows, and we are going to first, let's say that you want to copy a source row to a destination row. So the first step here, we're going to activate the first row. This operates exactly how I just mentioned. So the voltage, the charge that's stored in the DRAM cells perturbates the bit line, and the data, this amplifier senses that perturbation, and the data is latched to the sense amplifiers or to the local row. So this is just a regular DRAM access operation. Different from a DRAM access operation is that the next access that we are going to do is another activation to the destination row B. So this second activation, what it does is basically connects the DRAM cells in this row to the local bit, to the bit lines, and hence to the row buffer here. And since the row buffer is stronger, it's going to write back the data that is latched from the source row A down to the destination row B. So basically, this allows us to copy these 4 kilobytes of data from one row to another row without the intervention of the processor error. So this main idea of what we just did is to consecutively issue activates to the source and the destination rows inside the DRAM array. So this is just another view of what this is doing. So first we are activating the source row, the voltage or not the voltage, the charge stored in the DRAM cell perturbates the bit line. The sense amplifiers amplify the data to either VDD or to ground. The second activates to the destination row, connects the destination row, the cells in the destination row to the bit line into the sense amplifier. The sense amplifier which is going to get the data copy. The amplifier is stronger and is going to push the data that was previously latched to the destination cell, allowing them for the row copy. So if you do that, this mechanism is called row clone, and by doing that, we can significantly improve latency or reduce latency and reduce energy consumption compared to doing that copy using the CPU itself. So there is more on row clone, and what I just mentioned before was again initially done on simulation, and we saw and later on some people experimented a commodity off the shelf DRAM chip, so DRAM cell chip that you buy in the market or they have on your laptop or in your desktop computer, and then they saw that by violating DRAM time parameters, you can do these row copy operations already in current DRAM chips. So it's not specified like that, but if you can do that operation. And we built on top of that this PyDRAM framework, which is this FPGA-based prototype for doing this type of processing DRAM operations in an easier way. So it's a view of our prototype. We have an FPGA board with some RISC-V processor, and this being-enabled DIMMs that can they are going to be operated by violating DRAM time parameters. So basically, we implement this row copy initialization in this PyDRAM system, and then using again commodity of the shelf DRAM, and then we see that we can do this row copy and improve throughput and reduce energy. So yeah, the source code is available in the papers in our archive, and if you have more interest, you can check or this video, which Atabrek gave a lecture on it. So this is not the only thing that we can do in commodity of the shelf DRAM chips. So we can also implement other Boolean operations by also violating the DRAM time parameters of commodity of the shelf DRAM chips. And we recently, Ismail was sitting over there, we presented this his paper in HPCA 2 weeks ago, which shows that the functional completeness of this process using DRAM systems. So the main takeaway that we did from this paper is that we experimentally demonstrate with several commercial off-the-shelf DRAM chips for main memory manufacturers, and then we see that by following that similar approach, by violating DRAM time parameters, we can implement functionally complete Boolean operations like NOT, NAND, and NOR, and also up to 60 input and NAND or and NOR operations. We characterize the success rate of these operations using 256 commercial off-the-shelf DRAM chips for 2 main manufacturers, and then we observe that we can achieve really high success rates of doing these Boolean operations for current DRAM chips, and that the data pattern and temperature only slightly affects the reliability of such operations. So this is just to highlight that DRAM, by operating DRAM in a different way, we can do many more things other than just storing data. So there are many improvements on top of this row copy initialization operations for row clone. So for example, we can move data efficiently across different DRAM subarrays using Lisa. We can enable data movement at smaller granularities using Figaro. We can have better interbank communications, and we can do other computations as Boolean operations using Emmet. So I'm going to briefly skip Lisa, and I'm going to talk about Emmet, which enables you to do indirect and or not a majority operations following the similar principles than row clone. So this can be done by manipulating the analog operating capabilities of DRAM, and the main idea here is to activate 3 DRAM rows at the same time for computation. This is also, the operation was also being implemented in different memory technologies. So the way that these Boolean operations are done inside the DRAM chip is basically we activate 3 DRAM rows at the same time. So when you activate 3 DRAM rows at the same time, all of the DRAM cells from those 3 DRAM rows are going to simultaneously perturbate the bit line. And the simplifier circuit that we have over here is a differential circuit, which basically is going to amplify the voltage level to the majority of the voltages levels that is stored in the 3 DRAM cells involved during the triple row activation. So here in this case, since the first 2 cells have VDD over 2, they also have VDD and one has a ground. The voltage level is amplified to the majority of the 3, which is VDD. So basically, the final state that we have by doing this triple activation is AB plus or BC or AC, which by controlling one of those rows, so this control row C, we can either do A and B, or A or B, or A and B. So we call those operations book bitwise operations. And the semantics is we are performing those bitwise and OR operations of 2 rows and storing the result in a third row. So the way that this is done, so first you copy the rows to some temporary rows, and then we activate the 2 rows at the same time, and the result is stored in the temporary row. So this was initially proposed in this call 2015 paper, and later on elaborated more in this micro 2017 paper. So we can do and or operations by doing this triple row activation. And now you need to be functionally complete, we need to do also not operations. And to do not operations, so if you look at the design of the amplifiers, you can see that it's basically 2 back-to-back NOT gates connected together. So we can basically redirect one of the outputs of the NOT gates to a DRAM cell, and then based on that we can have the NOT version of the data store in the DRAM cell initially, allowing us to do now and or not operations, which is logic functionally complete. So yeah, this is just an example of how the not operation works. And basically, we see that we can achieve really high throughput compared to CPUs when you are doing this bitwise and or not operation inside the DRAM. And we can also significantly reduce energy compared to currently CPU systems. So we also look at several different applications, and we map them. And those applications basically uses those book bitwise operations, like database applications, heavily use book bitwise operations for filtering queries. And this is one example of query execution using this system. And then we see that significantly improve performance compared to the CPU implementation. So if you are interested on this book bitwise execution engine, we have this book chapter that elaborates further on the implementation details of it. So okay, we can implement row copy, we can implement initialization, we can implement book bitwise and or and not. What about more complex operations like arithmetic, addition, or multiplication operations? So you also can implement such operations by composing different triple row activations and row clone operations together. And this is what we did in this SIM-DRAM framework. So the SIM-DRAM framework is composed of 3 main steps. So the first step basically takes a given computation. So this is like, for example, addition, and it converts this addition into majority gates, because basically what we will have when you're implementing a triple row activation using DRAM activation command is the CS amplifier operating as a majority gate. So you do this conversion, and after that we generate the sequence of DRAM commands that translates to the circuit that uses majority not logic into row clone and triple row activations, and we call this a microprogram. So the microprogram is stored in main memory and also added to the ISA of the processor. And we have a third step, which is a control unit, the memory controller, which is responsible to translating the operations or to dispatching the operations in the microprogram to DRAM, and hence implementing the arithmetic operation that you want, like the addition or multiplication. So I'm not going to elaborate further to the time on the SIM-DRAM framework, but as I said, basically there are 3 steps. The first step is generating this majority not graph and optimizing it. The second step is translating the majority graph into these micro programs, which requires you to allocate DRAM rows for computation and also finally generate the microprogram. And in the third step, we have this control unit, which is placed in the memory controller, which is basically dispatching the different DRAM row activations to the memory, to the DRAM chips, in order to implement the initial majority not logic that was designed or was the user want to design. So by doing so, we also have to handle some system integration challenges. So by using this framework, we implemented 16 different in-DRAM operations following ambient and row clone. So we have addition, multiplication, division, subtraction, min, max, some equality checks, ReLU, bit count, and some others. And then we take those 16 different primitives and we use them to accelerate 7 real-world applications. And we see that by doing so, we can significantly improve energy efficiency and performance compared to a CPU and a GPU. And all of this is the SIP-DRAM paper. And we keep doing work following up on SIP-DRAM. And this work involves several things. For example, improving the computing granularity of SIP-DRAM, of processing using DRAM operations, some challenges related to the layout conversions, high latency for bit 0 operations, and basically this is a new paradigm or is a new type of system, and we are taking one step of a time, addressing all of those challenges in a more holistic, in the end, to have a more holistic solution. So the other, so one of those challenges that is mentioned here is this computing granularity of processing using the DRAM operation. So for example, when you do addition, following what I just mentioned before, using these triple row activations and row cloning operations, you are doing the addition over entire DRAM row. So in DDR2 chips, the entire DRAM row is 4 kilobytes of data, and in DDR4 is 8 kilobytes of data. But what happens when you have real applications is that often you don't have 8 kilobytes worth of data to at a given with a single operation to compute the addition. And then what we end up doing is that you pad the remaining portions of the row with zeros, so that we can fit the data inside the DRAM row itself. So this causes simulated underutilization for this processing using the DRAM engine, which leads to throughput and energy waste. Another problem is that you can add one row with another row together, but you cannot add a single row with itself. So if you have a vector and you want to do a scalar reduction to basically have a vector and you want to reduce it down to a scalar value, you cannot do that because there is no way for you to move data across the different DRAM columns inside the DRAM array itself. And the third problem is that it's really challenging to program these systems because you need to manually map these addition operations and subtraction operations to these pin primitives inside your application, which involves things like manually doing loop unrolling or orchestrating data movement inside the application. So as a summary, even though these processing using DRAM architectures are quite efficient, they suffer from this granularity problem of computation. And we did this work that we also presented in HPCA recently, which its goal was to design a flexible processing using DRAM system that overcomes those 3 limitations. So to this end, we proposed this system that is called Memory-DRAM, which its key idea. So again, it's just an overview of a DRAM subarray. So we have here I have another view, and inside this DRAM subarray we have what's called DRAM max, and we have this global word line that's spread across the different DRAM max. So when you do a DRAM row access, all of the portions of the rows across the different DRAM max are all accessed because the row decoder drives all of the maps together in a DRAM access. Even if you're only going to access a small portion of the row later on for a cache access, for example. So there is this concept that's called fine-grained DRAM, which segments the global word line, allowing you to access individual portions of a DRAM row for computation. So this has been proposed several times to improve energy efficiency of DRAM systems, and we are going to do the same. We are going to use the same idea for this processing using DRAM operations, which provides 3 main benefits compared to the state of the art. So the first one is that for a single operation, we can improve simple utilization of computation. So when you do a process using DRAM addition operation inside DRAM, for example, we can only access the portions of the DRAM row that actually contains the data that you want to compute over. So this improves energy efficiency and throughput of the system. Second, if you have multiple operations targeting different portions of that DRAM row, you can, and they are independent, you can execute them at the same time in a multiple instruction, multiple data execution model. Again, improving overall system throughput. Second, we can leverage the internal interconnect inside the DRAM array itself to move data from one portion of the DRAM row to another portions of the different of the DRAM row in a different method, which allow us to implement that scalar operation that I said, the vector reduction into a scalar value that I mentioned before. And third, if when you look for one of these structures, these DRAM mats, we see that we have usually 512 to 4 by 1000 or 512 by 512 rows and columns, which is a similar granularity than vector ISAs from, for example, Intel EVX 512. So you can map those instructions for processor vector ISAs to instructions of this to execute inside the DRAM chip itself. So following this key idea, we propose this MIM-DRAM, which is a hardware software co-design process using DRAM system, which has both hardware and software components. So briefly on the hardware side, we basically propose some modifications inside the DRAM array to enable us to access individual portions of a DRAM subarray, and we have the some low-cost interconnect that allow us to move data across adjacent DRAM mats. We also have an implementation of a control unit, which is basically responsible for scheduling and keep tracking of which portions of a DRAM row are being used for computation, and a compiler support that is used to translate C code down to those book bitwise addition and multiplication operations that are going to be executed inside the DRAM subarray. So we evaluate this system using 12 applications compared to a CPU steam DRAM, which I just mentioned. In DRAM, we can significantly improve energy efficiency. So for more that, I invite you to check our paper. And so basically, as revisiting what you just type of operation that we are doing. So we did row copy operations, we did initialization operation, book bitwise and the NOR operations, arithmetic operations at large and smaller granularities. And there are even other things that we can do. For example, we can do these DRAM lattice puffs for physical unclonable functions inside the DRAM array itself, or we can generate true random numbers by inside the DRAM chip itself by following this multiple row activation procedure. And there is those two works, and this is an end-to-end system to enable or to make use of those two random numbers. And finally, we can also implement other transcendental functions. For example, sine, cosine, logarithmic square root operations in a similar way inside the DRAM using lookup tables. So this is just a summary of the type of operations that I just mentioned before. So data movement, Boolean operation, arithmetic operations, and shifting operations. But still, prior work was not covering transcendental functions like sine and cosine functions. So we implement these functions in this project or in this group that's called Pluto, which basically is going to use this key concept of lookup tables for processing using DRAM computation. So lookup table base is before doing any computation, we do the computation once, and then we store the result of this computation into table. So if you think about sine or cosine table for different angles, we basically store those angles, the sine cosine values for the different angles inside that table in DRAM. And instead of computing the sine and cosine, we just look inside that table for a given angle value for a given sine. And this is called lookup table. queries. So basically here we are replacing computation, so we are not computing and we are not executing time series or Taylor series operation to go put sine or cosine. We are querying the memory with a given angle to get us the sine cosine value. So this is this Pluto system. On top of that, we also implement some system support to generate, translate instructions down to this lookup table queries operations. And then we see that in terms of performance, again, we significantly improve performance compared to CPU and GPU, and improve energy savings as well. And all of that is in this paper. So, as a summary to quickly wrap up, over here I discussed two different types of memory-centric architectures. The first one is this processor-near memory architectures, which again is adding logic to the memory device to do some computation, and processing using memory architectures, which are using the analog operating principles of memory cells to perform book-bitwise Boolean operations, row copy operations, or arithmetic operations. There is still several barriers that we need to mitigate or to address in order to fully leverage or to fully adopt processing memory architectures in current systems. For example, we need to look at applications and software support for processing memory. We need to find better ways or better interfaces to program this type of systems. There is some concern related to also to security. To run times and scheduling and data mapping and allocation for those systems, and overall infrastructure to assess the ability of those systems for different applications. So all of this can be done and can be if you change your mindset and are more open to changes to current processor designs. But to do that, we need to again to revisit the entire compute step one thing at a time. So this is just a summary of the works that we have done so far in that direction to enable processing memory. So for example, how to do bare minimum modifications to the DRAM array and enable some computation, how to use programmability, how to maintain data coherence, how to enable support for synchronization, how to enable virtual memory, how to enable code and data mapping, analysis methodology and workload for a processing memory system, which I'm not going to cover right now because of time. I'm going to skip to the slides. Also, and we keep working on this type of system. So in the MIM-DRAM work that I just mentioned, we deal a little bit with this compiler support for processing memory as well. And there are still many other challenges like virtual memory, data allocation, data mapping that needs to be overcome. To wrap up, what we want for the future is fundamentally more energy efficient architectures, which are data-centric. We also want high-performance architectures and architectures that compute with minimal data movement inside the system. In order to do that, we need to design more balanced systems or more intelligent systems, which are data-centric, data-driven, and data-aware. And overall, we can do that by enabling computation inside or closer to the memory, which can lead us to significantly improvements in terms of performance compared to current processor-centric systems, enable new applications and application domains, better understanding, which enables us to better understand systems and data overall. So overall, there is a bright future for memory-centric computing, especially because of this push from industry that we are having right now. So many big companies investing a lot of money in this new way of doing computation. So it's quite a promising new paradigm and a promising direction for memory-centric computing architectures. Again, to do this, we need to revisit the entire stack and be open-minded. Again, if you are interested on further discussions on all of those topics that I mentioned here, I invite you to check our ping book chapter, and also we have some lectures online covering all of this process memory concepts. We have classes here in ETH in previous semesters dedicated only for processing memory systems. Also tutorials in major computer architecture venues for real processing memory architectures. So the last one was in Micro 2023, and we have a follow-up one in ISCA 2024. So if you have one more reference or information, you can check in our web page or in our GitHub. So you're going to have infrastructure that can be used to evaluate or to analyze these process memory architectures. So we are just on time. So thanks so much for your attention. And if there is any question online or here, you're done.
There is no question on YouTube, but I don't know which context is this. Can I model this architecture on an FPGA? Probably the memory-centric architecture.
You can, yes. So we have actually in your web page, you can look for Nero, which is a FPGA-based system, FPGA-based processing near memory architecture that we did using this IEDM architecture in order to accelerate weather modeling, genomic analysis, and also stencil computation. So you can do that, all of that in FPGAs. And if you want to model processing using memory, we have also this infrastructure called DRAM Bender. That is, you can check that HPC 2024 paper from Ismail. So is already in archive, and over there you're going to find a reference to this DRAM Bender system, which can be used to evaluate these processing using memory architectures using FPGA-based systems. So yes, so the answer is yes for both.
Thank you.
Sure.
Could you maybe explain again a bit how the operations in terms of using memory, like where do they happen? So if I want to, for example, do an add of 2 rows, like where is this?
Let me go back to the illustration. I guess I went too fast over there. So what is happening is, so we start by having 3 DRAM rows, A, B, and C, and all of them store some charge level. So A stores VDD, B stores VDD, and C stores ground. So if you activate all of the 3 DRAM rows, or you read all of the 3 DRAM rows at the same time, what is going to happen is that the charge that is stored in these 3 DRAM rows at the same time are going to perturbate the bit line to a voltage level, which is delta. And the circuit here in the sense amplifier is a differential sense amplifier. What it does mean in this context is that it's going to amplify this perturbation to the bit line voltage to the majority of the voltage levels stored initially. So the majority of the initially stored data was VDD, VDD, and ground. The majority is VDD. And then basically, after this amplification is done, we have the output of this majority stored in the 3 DRAM rows at the same time. So I don't know if it was more or less clear.
So these 3 rows are like any rows.
Any rows, yes.
And the circuit here is like just once in the entire memory somewhere.
Is replicated across the many DRAM columns inside the DRAM subarray. But yes, and this circuit again is not you're not adding this circuit already exists, and this procedure is already what's happening when you access the DRAM array itself and your computer or in your cell phone. The only thing that your computer does not do is this triple row activation. It only activates 1 row per time. But basically, if you are a little bit smarter and activate 3, you can do this majority computation because of these operating principles of the DRAM cells.
So I was wondering if instead of this, we could do something like, instead of having like this 1 bit line, we would have 2 or 3.
So inside the DRAM row, actually, so this is just one, yeah. But inside the DRAM subarray, we have around 65,000 of those. already there. Together with the circuit here. So they don't share the circuit. Each one of them is an individual one. So you can do 65,000 of this majority at once.
Yeah, like I understand that this is like replicated in parallel, but like that you could like separate, like separate the signal from A, B, and C into like 3 separate bit lines, and then instead of having this circuit, like actually have like an adder or something like that, so that you don't have to do this translation and just have.
That will be more efficient for sure, and then there are works that propose to do something similar to that actually. The problem is that this including logic inside the DRAM chip itself is quite a challenging manufacturing process, and it's really costly actually. And also not only costly, it affects the performance of both the memory and the performance of the logic. So basically you get the worst of both worlds when you mix computation and logic together. So this is why one of the reasons that the first thing that I mentioned before, the processing near memory, took so long to take over. Because when you are actually trying to manufacture that thing, we are manufacturing a really inefficient system. So because of other technology advantages, like this 3D stacking, for example, we can now manufacture those things, but because they are manufactured separately and then later on we put together. Here, since this is inside the smaller granularity that we have inside the DRAM chip, which is a DRAM subarray, it's really hard for you to manufacture the logic and the computation separately and then merge them together, because when you're manufacturing, just like everything is really packed together inside one single unit, so you can improve the capacity of that chip. So yes, you can do that more efficient. It will be more efficient because you will require less steps to do computation, because you can have either, for example, as you mentioned. But at the same time, it has quite a high cost in terms of performance, and not necessarily performance, but in terms of area costs and manufacturing challenges to do that.
Yeah, that's okay.
Okay, if there's no other question, thanks so much again. And